Okay, good afternoon. I'm Davide Poli, and today we'll talk about advanced 2D fluid modeling of all-effect thruster discharges, supervised by Pablo Fajardo and Eduardo Ede. I will skip the description of how a Hall thruster works because you've already seen it in previous presentations, and I'll go directly to the motivations, which is the study of the anomalous transport using fluid modeling. Anomalous transport is the enhanced axial mobility of electrons, which cannot be explained by classic collisions. Possible causes are given in near wall conductivity or in the onset of plasma instabilities, and this is what I will analyze with my codes. The objective of the thesis is to analyze axial instabilities and azimuthal instabilities. So as a brief recap for what I did in my first year of PhD, I developed a one-dimensional quasi-neutral time-dependent model of a Hall thruster. You can see the computational domain there on the right. Here we have the anode and going towards the far plume. This model introduces a series of novelties in the frame of time-dependent models, such as a volumetric cathode, introduction of azimuthal electroinertia, and the complete characterization of neutrals dynamics, and in general also heavy species by the inclusion of ion energy equation. Some results from the first year were the assessment of the importance of a proper neutral modeling and the importance of the azimuthal electroinertia and the dynamical behavior and stationary behavior of the thruster. This year, I pushed forward analyzing the breathing mode, the ionization instability, and for example, you can see on the right a parametric map where we have three possible conditions of the simulation, which is a stationary regime, the breathing mode, and the shift collapse. The shift collapse is when basically the model fails, and that's because we're going towards a reversed sheath condition at the anode, where the anode passes from being electron repelling to electron attracting. The model currently cannot sustain a reversed sheath or no sheath condition, and so the simulation simply fails. And this will be assessed with a more versatile or robust sheath modeling. What's interesting here, where we have on the y-axis the energy input for neutrals coming from the wall, because when an ion hits the wall, it recombines and re-enters the bulk of plasma as a neutral, retaining part of the energy of the ions prior to strike. And on the x-axis, we have the anode magnetic field intensity. What we can see is that there is a relationship on the onset of the breathing mode with these two, let's say, parameters. And this is not something trivial, because in the literature, for example, neutrals dynamics is completely disregarded and it is not considered in the study of breathing mode. We can also see that increasing the magnetic field, it is more and more difficult to obtain an oscillatory solution. I still don't know why. We'll be doing more analysis in the future, but what is clear is that what has been done in the literature so far is not comprehensive enough to understand and isolating the trigger method of the breathing mode. And in general, we saw also that it is extremely difficult to isolating this trigger with one-dimensional models because of all the simplification in the physics and the parameters that we use. Going on with the 2D model, this year I've been developing a two-dimensional axial azimuthal model of a Hall thruster. Here you can see the computational domain, where we have the anode here and the far plume, a volumetric cathode, and periodic boundary conditions. This because this computational domain corresponds to unwrapping the cylinder corresponding to this dashed line into a Cartesian domain. The model for now is uses full electron inertia and considers a non-neutral plasma. Possible future development are going towards quasi-neutrality and rift diffusion. Quasi-neutrality because resolving the Debye length imposes very strict, a larger number of cells and very strict timing condition for the CFL condition. So quasi-neutrality could be beneficial for computational time, but it is difficult to obtain a solution with quasi-neutrality in large Hall parameter conditions because the equations are ill-conditioned. These are the equations that I'm solving with this model, which are general multi-fluid equation, can be used for ions, electrons, and neutrals. Of course, for neutrals, they don't have charge, so this term is zero, and these are coupled with the Poisson equation. These are basically Euler equation with some source stiff terms on the right-hand side. To solve this, I developed a two-dimensional finite volume codes from scratch in Fortran, which uses a structured mesh with MPI domain decomposition, and we can select between different approximate Riemann solver, reconstruction techniques, and integration schemes. Latest addition to this code is the ability to expand plasma or gas in general into vacuum. So this is a first preliminary test on a Hall thruster simulation. In this case, I'm using a full electron model, while for ions, I'm not considering the energy equation, and for neutrals, I'm only considering continuity. Starting with a volumetric cathode probably wasn't the best idea. That's because the boundary conditions are somehow more complicated and all the numerics is more unstable. So is this is a electric field on this multiple direction, and this is the electron's temperature, where the instability is particularly visible, but it affects also density, of course, and velocities. But is this a physical or a numerical instability? I still don't know yet. I have to do more testing, more appropriate boundary conditions, and something that I will do is to exclude the volumetric cathode and use a planar cathode. So shrinking the domain up to here, so that I can compare this model with the global stability analysis performed by Enrique. Another thing that I've been working on in this period is a penny discharge simulation. This because rotating spokes are not a unique features of all thrusters, but are common in equal-speed devices in general, such as planar magnetrons and penny discharges. Moreover, Enrique was working on the penny discharge with his PIC code, and we thought, since this is a fluid instability, it would be nice to compare the particle in cell code and the fluid code to see whether we see the same things. Well, unfortunately, this is a very difficult scenario for a series of factors, among which the extremely low densities that we reach due to the magnetic confinement at the boundaries of the domain, and the fact that this is an all-Mach flow with shocks, which could be physical or not, and the fact that, in general, these problems are solved in fluid dynamics by adding a little bit of numerical diffusion. But if we do that, the instability is not arising anymore, because we are adding some transport, let's say. After many attempts, such as positive preserving schemes, a posteriori correction, I found out that a vacuum tracking algorithm manages to solve more or less this problem. And as you can see on the right, after a chaotic transient phase, which I cut for sake of time, you can see the formation of a single spoke M1 rotating in the equals B direction. This solution is somehow contaminated by what I think is reflection of shock waves at the corners, the domain, which means that probably I should work a little bit more on boundary conditions. So for future works, I plan to optimize better the code and improve numerical schemes, for example, HLLC Riemann solver and a piecewise parabolic method. I plan to do many more, of course, all thruster simulations and compare with the global stability analysis of Enrique. And for what concerns the 1D model, I plan to finish my non-neutral version of the model so that I can capture self-consistently the sheath and then compare what happens in the sheath vanishing regime with the non-neutral and compare the two solutions. I hope to write articles, plural possibly, and to organize a research stay. These are my scientific production for these 2 years. I presented at the SPC last year, and I submitted this year an article on the one-dimensional model, and I will present the results on the penny discharge at the ICPIC conference in July. Thank you for your attention.